Hello, assalamu alaikum everyone. So this is the last lecture of the course, and this is lecture 19th, which covers the second part of the different routing protocols that we're supposed to cover. So in the last lecture we learned about two different routing protocols, and in this one we're going to learn two new ones and also about VANET, or Vehicular Ad-hoc Network. Okay, so let's start. So the first protocol that we're going to learn is DSDV, Destination Sequenced Distance Vector Routing, and this is also a table-driven routing protocol for ad hoc mobile networks, but it's based on Bellman-Ford algorithm, and DSDV primarily contributes to solving the routing loop problem. So if you remember, the Bellman-Ford algorithm was can actually detect cycles or loops by and also it can understand negative edges in the network. So if there are negative edges and there are loops, so even in those scenarios the Bellman-Ford algorithm works well, and it can detect those things. Okay, so these are the positive aspects of the Bellman-Ford algorithm. But the negative aspect was that it is very it has a very high complexity because it needs to relax every link. So it has very high complexity, but it can detect those things which other algorithms cannot. So this Bellman-Ford algorithm can be used to solve the routing loop problem, which is why it is used in DSDV. So each entry of the routing table contains the following columns. One is the destination, then the next hop in the path from the source to destination, then the number of hops, the sequence number, and the install time. Okay, so if you remember, in the last lecture we learned a protocol which had three columns in each entry: the next hop, the number of hops, and the sequence number. So those three are also present here, but extra values are, or extra columns are, the install time and the destination. So the next hop suggests which hop the packet will be forwarded to for a specific source to destination, and the number of hops tells us the number of hops required to reach the destination. And here the sequence number is not not only representing the freshness, but also it represents whether there is a link present or not. So if the sequence number is an odd number, it means that there is no link present, and if it is an even number, that means there is a link present. Okay, so the destination keeps the information or the address of the next of the destination, and it is used to determine the route for this node. Okay, so this is sort of what is used for matching the entry. So matching means whenever we compare a packet, the packet has a header which which identifies or shows where the destination is or what the destination is. So that is compared to this part of each entry to understand where to go. So the install time reflects how recent the current entry is. Okay, so these are the 5 columns of each entry. So this is an example of the 5 columns of the entries. The destination here represents the node. So as it is shown in short, but usually it contains the addresses, okay, instead of just A, B, and C. And the next hop column shows where to go for the next destination. So as this table is for the node A, so to go to the destination A, the next hop is also A because it itself is the destination, and the number of hops required is 0. So the sequence number is just a number shown here, and the sequence number usually also keeps the destination information. So as you can see, for the next row, the destination is B, so the sequence number is B36, and for the next line, the destination is C, and the sequence number is also C26. So all these are even numbers. That means all the links are present, and at the right we can see the install time. Okay, so it basically stores the time and during which the entry was let's say kept in the table. So for the destination B, the next hop is B, okay, because B is itself the destination and the number of hops required to go there is 1. And for the destination C, the next hop is also B and the number of hops required is 2. So we can clearly understand that A is connected to B and B is in turn connected to C. So if A requires to send the packet to B, it just directly forwards it to B, and if it requires to send to C, then it will forward the packet to B and B will forward it to C. So this is how we can understand who to forward the next the packet to and what is the final destination. So the distance vector routing uses Bellman-Ford, as you have already learned about Bellman-Ford in the previous courses, and I have also talked about it in short. So the sequence number generated is generated by destination, and it keeps the destination information, and emitted, that means that, let's say if there is an update or let's say if some node detects an anomaly regarding that path or regarding that route, then it must also use this specific sequence number to send the updates, so that everyone else can verify whether it is an actual update or not. And routing information is distributed between nodes using full information, but that is done very infrequently. That means it is not done regularly, because sending the full information is not necessary all the time, and smaller incremental updates are done frequently. Okay, so these are the two ways information is let's say forwarded to other nodes. So according to the DSDV protocol, if a router receives new information, it uses the latest sequence number to decide whether to select or whether to receive the new info or not, just like AODV, right? And if both the sequence numbers are same, then the route with better performance based on a routing metric, for example it can be a hop count, is selected as a new route. Okay, so if the sequence numbers are not same, that means the latest sequence number is selected, and if they're same, then the route with the better performance is selected. So entries without any update for a long time are deleted along with other routes which have the same nodes. Okay, why? Because if there is no update regarding a specific route or specific entry, that means that there is a problem in that route, and this is why no updates are received. So that route is deleted from the memory, and every other route which has those specific nodes are deleted. Okay, because we don't know which node has failed or which link has failed, so all the related nodes needs to be deleted so that a new route can be found, or it can be checked whether a new route is present or not. So this protocol is a bit old, but it has multiple advantages and disadvantages, and this protocol is used, or actually many protocols take lessons from this protocol. Okay, so so the advantages can be, if there is a path available to all network destinations, the path setup process has less delay. Okay, so the precondition is there has to be a path to all the destinations, and existing wired protocols can also be adopted to ad hoc wireless networks using incremental updates using sequence number labels. So if you remember, the incremental updates were done frequently, and they use sequence number labels to verify or to make all the other nodes understand that the update is valid. Okay, so this technique can be used for wireless networks as well, and wired protocols can be made effective in wireless networks using this technique. So it requires regular update of its routing table, so uses more bandwidth and power. Okay, even if the nodes are idle. So this is one of the disadvantages because of those frequent and infrequent updates or broadcasts. So for topology changes, new sequence numbers are necessary every time. So it is not suitable for highly dynamic or large scale networks, because in those scenarios there is either a large number of nodes for large scale networks, or the routes might be changing very frequently if the network is highly dynamic. Okay, so the sequence numbers or the limit of the sequence numbers might be very quickly reached if every time the sequence numbers are changed or if the topology is changed, okay, because that's how this protocol works. So although the protocol is not used today, the techniques are still used in recent protocols. An example is AODV, okay. So AODV uses some of the techniques that is used here. So it's not actually the other way around. Instead, AODV learns from this one, okay. So this is another protocol, and we are just going to learn about this in very short or in very brief. So this is the hybrid wireless mesh protocol, or HWMP, and the name clearly suggests that this is also used for wireless mesh protocols, and it is defined in IEEE 802.11s, okay. So if you remember, we had already gone through this protocol, right? And it is a basic routing protocol for wireless mesh network, okay, the 802.11s. So HWMP is actually used for that specific protocol. So it is based on AODV, and it is a tree-based routing, okay. So what it does is it discovers and tracks the neighboring nodes using a peer link management protocol. So peer usually means ones of the same level, so it suggests that it's talking about the neighbors, okay. So neighboring link management protocol, that's also how we can term it or phrase it. So it is hybrid, or the name says that it's hybrid because it supports two kinds of path selection protocols, and both are actually used in IEEE 802.11s, and it uses MAC addresses instead of IP addresses. So if you remember, MAC addresses are addresses based on the data link layer, and IP addresses are based on the network layer. So this protocol uses the MAC addresses instead of the IP address. So the two kinds of path selection protocols that it uses is one of those is based on AODV and is on demand. That means it only searches for routes if there is a packet which does not match any entry in the routing table. And the other protocol is proactive, okay. So that is proactive tree building, means it does not wait for a new packet, or does not wait for a packet which does not match with any entry in the table. It automatically keeps searching for destinations, or how to reach different destinations. So it is hybrid because it can use both simultaneously, or both modes simultaneously, okay. So that's it about this one. Next we're going to see some VANET routing protocols, okay. So the VANET is different from MANET because MANET means mobile ad hoc network. So it just means that the nodes are ad hoc and mobile, so they will be moving, and obviously they'll be wireless. But VANET means vehicular ad hoc network, so they are not only just mobile, they move very quickly compared to other mobile ad hoc networks, okay. And the mobility might be sudden. So it might be that the car is parked and it is there for a long time, but again it might suddenly start, and it might quickly change its location. So there are different kinds of routing protocols for VANETs, and they can be categorized into broadly 5. So as you can see here, position based, topology based, broadcast based, cluster based, and geocast based, okay. And they can also be again classified into different categories. For example, topology based can be classified into proactive, reactive, and hybrid, and the others are examples of the routing protocols. So let's see each category one by one. The first one is position based, okay. So in this protocol, the geographical position is shared along with the network location. So for routing we need network location, right? But in this scenario, along with the network location, it also shares the geographical position. So beacons are transmitted regularly to let everyone know about the position of the node, and there are 3 main components of this protocol. One is beaconing, which is letting everyone know the current position, and the location services. So in order to let everyone know the current position of a node, the node itself has to know its position, okay. So this is why the location services is required, and also forwarding capability. So without forwarding, actually it's not a network. So it requires global positioning system, or GPS assistance, to decide the location of the various nodes. And examples of this routing protocol can be distance routing effect algorithm for mobility, or DREAM, and greedy stateless routing, or GPSR. So we can see a figure on the left which shows an example. So the left vehicle is actually sending a query message, and it's a query about the identification, sequence number and hop limit of another node, and the node is replying with a location reply message. Okay, and before that it also has to check whether it's a duplicate message or not. Otherwise, for every message it gets, it might keep on flooding the network. So after the duplicate check is done, it replies with the message, the current position and the timestamp. Okay, so this is how the position based networks communicate, or nodes in the network communicate. So next is the topology based protocol. So this uses the available information about the link of the network to forward packet from source to destination. Okay, so this is only possible if the topology information is known, which is usually not the case, because vehicular ad hoc networks have nodes which move very quickly. So there are mainly three categories of topology based routing. One is proactive, reactive and hybrid, as we have already seen in the previous figure, in the previous figure. So the proactive routing usually depends on the shortest path algorithms, because those algorithms actually calculate the distance to the destinations, to all possible destinations, without waiting for any query, and uses standard distance vector routing protocols like DSDV, which use those shortest path algorithms. And reactive routing, on the other hand, only performs routing when a packet arrives. So it's sort of like on-demand routing, and it decreases the protocol overhead because it only searches the entire network when required. Otherwise, it only maintains the already existing routing paths. So examples of reactive routing can be dynamic supply routing, or DSR. Hybrid ad hoc routing combines these two, proactive and reactive routing. So it divides the network into local and global regions. So the local regions are following proactive routing, and the global regions are following reactive routing protocols together. For example, zone routing protocol, or ZRP. The next category is broadcast based. So this sort of protocol floods the packet over the entire network in a broadcast domain, and hence the name broadcast based routing. So whenever the node is outside the transmission range, this method is used, because the exact location or the exact path is not known. So it forwards the packets to everyone who is in close proximity, and they in turn forward the packet so that the intended user or intended vehicle can get the message. So this is mainly used for safety related applications, for example climate, traffic, road conditions, etc. Okay, so these messages are very important because they are safety related applications. So instead of taking risks, the broadcast method works very well here, because the broadcast is almost certain to reach the destination, and this is the kind of information which every vehicle needs to know. So the broadcast based protocol is the best used here. And example of this category are distributed vehicular broadcast protocol, or DVcast. The next protocol is, our category is cluster based. So vehicles having similar characteristics, for example, let's say cars having the similar velocity, and maybe they're going in the same direction, or they're going together or grouped together. So in those scenarios, the cluster based protocol is used, and each group of vehicles forms a cluster, and communication is managed by the cluster head of that cluster. So if a packet is in the same cluster, or the source and the destination both are in the same cluster, then it can be directly sent. That means the source can directly send the data packet to the destination. However, when the destination is outside the cluster, that means it's, let's say, in another cluster, so in this scenario the cluster head provides a scalable system. So this means that it can be different kinds of scenarios, or it can be a different kinds of systems. For example, the vehicle might carry, or the cluster head might carry that data packet until it reaches a place where it can forward it to someone of another cluster, or it can probably send with a high power signal if the other cluster is nearby. So examples of this category is clustering for opening vehicular communication network, or COIN. So this is the last category, which is geocast based routing, okay, or geocast based vehicle routing for VANET. So it uses Mobicast messages to communicate with vehicles. So Mobicast is a specific type of multicast technique which can be used to communicate with multiple nodes at the same time. So there are two kinds of Mobicast actually, so do not confuse them. This is one of those types. So communication happens at a specific time and in a specific region, okay, and that region is called the zone of relevance, or ZOR. So whenever the vehicles are in the zone of relevance, then they communicate with each other. So if the destination is not in the specific ZOR, the communication is done using a zone of forwarding, or ZOF, okay. So whenever a vehicle you want to send, that means the destination vehicle and the source vehicle are not in the same ZOR, it has to be done by going to another region which is called the ZOF, and any car in the ZOF has the responsibility to forward the packet to other ZORs, okay. So like this, the packet from the source can move from ZOR to ZOF and then again to ZOR, and like this until it reaches the destination. So example protocols are IVG, DGcaster, etc. okay. So these were the different categories of VANET routing, and there are some references here as well so that you can look up those protocols. One for the destination sequence distance vector routing, or DSDV, and the second one is for hybrid wireless mesh protocol, or HWMP, and the third one is for hybrid, the same as before, but instead of Wikipedia, this is a research paper. And the last one is for VANET routing protocols. The last 5 categories that we read can be found here, okay. So that was about it, and if you have any questions regarding this lecture or any other lecture before this, you can ask. And I guess this is the end of the course, and this is the last lecture of the course. So yeah, okay then, assalamu alaikum everyone.